Now let's look at 10.8 on Taylor and Maclaurin series. So what this is basically is a series, an infinite series expansion of a function in a summation form. Allows us to work with a function in different ways. Okay, so this time I wrote everything out because there's a lot of little details that would have taken a long time. All right, so you can pause it and copy as you go. So first is called the Maclaurin series. So we say if f has a power series representation, right? So you have some sort of power series for the function that has a radius of convergence r, then f to the k, meaning f, the kth derivative at 0 exists. So it's expanding like around 0 at 0 for all k. So the derivative exists for every value. And it tells you what each term is. So you can write f of x in this form. Now, if it's, if it's simple, then like you get 0, then it's not very interesting. But considered like sine, cosine, e, then this type of expansion would be very useful. Okay, then you have, so it's f of 0, f prime of 0 times x plus f double prime of 0 over 2. And notice you end up getting this form, f to the nth derivative of 0 over n factorial. So that's a sub n times x to the n, of course. Okay, so this is the Taylor series. We call this Maclaurin series. Taylor series is really the more general case. This is what we call centered at c, or some constant. Then f of x has this form. And so it's just, remember, it's just like you would be centered at x minus c. In fact, that's probably what that needs to be, that actually. So this is x minus c. Okay, then you have this expansion of the function at c. Okay, so Maclaurin series is basically a special case of the Taylor series. So Maclaurin is just Taylor with c equal to 0. Okay, so let me just show you what this looks like. It's easier to see kind of as you do once you do it. And we're going to kind of keep it simple. We're not going to get into a lot of this, the error and all that kind of stuff. So going back here, just in this chapter 10.8, focused on these problems, 1 through 40, page 625, and we're going to skip 10.9. I think I did assign that for homework, but you can skip that. So just focus on these types of questions. So basically it's conducting an expansion, or creating the Taylor or Maclaurin expansion. So let's look at this example. Let f of x be cosine x. Find its Maclaurin series and find its interval of convergence. Okay, so first thing you'll need to do, so if you go to Maclaurin series, it's basically this with c being 0. You need to find its derivative. All right, so as you go, first derivative, second derivative, all the way to the nth derivative. Now, for cosine and sine, it's going to be cyclical. Right? It's going to start repeating. So let's go through and do it. So here's f, first derivative, second, third, fourth, fifth. So it starts repeating after, so 1, 2, 3, 4, and then you're repeating, right? You repeated back to your cosine. So every fourth derivative, it's repeating. Then you evaluate at 0, right? Because it's Maclaurin series, it's at 0. So you evaluate at 0, and you get this expansion. or these values, I'm sorry, 1, 0. So every other term is going to cancel out. So this is the expansion. You have f of 0, f prime of 0, and then f double prime, triple, right, etc. And you can see then that the odd, this is odd, 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 derivatives are 0, so they cancel. So this is n equals 0, 2, 4, 6, etc. So you get this expansion for f of x. Okay, we can find, so that would be the question, essentially. We can find sine x in a similar way. Okay, but can you think of a simpler way to calculate once you already know cosine x? So think about that. I'll show you down here, but okay, so just a little side note there. The other part of the question was find interval of convergence. All right, so to do that, we need to do what we've been doing is applying the ratio test. So we apply the ratio test, and I just realized I ended up copying this whole thing when I meant to just, I mean moving this whole thing. I meant to just copy it, so I'm going to put it back. Okay, so it needs to be there. So u sub n is this, right? That's this right here. And then u sub n plus 1 is at putting plus 1 for all the n's. N plus 1, n plus 1, n plus 1. And then you do the ratio. Okay, so u sub n plus 1 over u sub n. Okay, so here's your u sub n plus 1. And then you invert and multiply. And then you reduce. So this takes some work to look at how to reduce, but you have to do 2n minus 1, 2n minus 2. This will be 2n plus 2. So it'll be 2n plus 2, and then you do minus 1, minus 2, etc. Okay, so we simplify this. So take a moment to see how it simplifies. And then you take a limit as n approaches infinity. So, and again, I've said this, I think, before. When you leave this off, it's implied it's approaching infinity. Okay, so if you approach infinity for these two, remember you're considering x to be something fixed. So x isn't moving. X is fixed at some value. It could be a large value, it could be a small value, but it's essentially a fixed value. It's n that's approaching infinity. So this denominator is approaching infinity, numerator is fixed, therefore it equals 0 as you approach infinity. So that's less than 1, obviously. So therefore it converges for all x. Okay, so that's the convergence you get for every value of x. Okay, next was an example applying some of the properties. So approximate the integral sine x squared dx to 4 decimal places. And in the 10.9, you get more into the convergence and error approximations. Oh, you may want to look on a little bit on that just to see what it says, because you'll do more of that later if you continue in your math. But we're just going to look at this today and this semester. So consider this, though. There's no way to do this antiderivative, right? If you have sine x squared, there's no way to get your x back here. So an explicit form, we'll try to figure that out. Like an explicit form might be pretty difficult, if not impossible. Okay, and that's another discussion. But what you can do is do a Taylor expansion. Okay, so you can expand this for sine. Well, actually, this is a Maclaurin expansion because it's at 0. And so expand sine x, so this is in the book, or you can look it up. It's one of those ones you need to know how to prove, kind of thing. So do your sine x. So notice these are odd now. Okay, so you get sine x, and you can show that that's true for all x. So then substitute x squared into that expansion. Okay, by doing so, you get this expansion. So that's your function value in your integrand. And so now do the antiderivative of each one of those terms. Okay, so when you do that, you get, let me take this away here. So you integrate each of the terms. And then you would be evaluating, oops, wrong button. From 0 to 1, right? So we integrated each one of those. I didn't really show that step so much. Integrating each one of those, you're getting this, right? Add 1, divide, add 1, divide. It's a polynomial, so you can easily do that. And then if you simplify this, now when you evaluate, you're just plugging in 1. It's a polynomial, so it's just 1/3. So there's your 1/3. And then 0 zeroes out everything. So you're really just evaluating at 1. So you get 1/3. This is 1/42. That's 5 factorial times 11. 15 times 7 factorial. And when you do that calculation, you get this value. And then you can talk, well, this isn't really what we got into. Maybe check it out. The error calculation is the difference between each successive term and how it converges. So this is basically 4 decimal places. Didn't even need this term, basically. Okay, so look at those types of questions, be able to do simple stuff with sine and e to the x and cosine, some basic trig type stuff for these questions. And that wraps up chapter 10. That's all we're going to do in chapter 10. There's 2 more sections. One was not originally scheduled anyway. 10.10. So we have one more chapter to go, 10.6. So this 10.6 is on parametric equations and conic section, or parametric equations and polar coordinates. Okay, we'll get to that this weekend, probably, definitely next week.